In metallic automotive coatings, face, flop, and travel are not subjective styling terms. They are measurable optical outcomes governed by flake orientation, film structure, and controlled solvent-driven film formation. Understanding these effects is essential for translating formulation intent into OEM-approved appearance performance. Face describes the color and brightness observed at near-normal viewing angles, typically close to the specular reflection direction. At this angle, light reflects predominantly from metallic flakes oriented parallel to the coating surface. High face brightness requires a high population of well-aligned flakes near parallel to the surface, minimal surface roughness, and sufficient film continuity to prevent light scattering. Early solvent evaporation that increases viscosity too quickly reduces flake mobility and leads to reduced face brightness and muted color strength. Flop refers to the change in lightness and hue observed at high viewing angles away from specular reflection. Flop is governed by the angular distribution of metallic flakes through the film thickness. A controlled gradient of flake orientations allows light to be reflected at multiple angles, producing strong brightness change from face to side angle. Poor solvent balance or unstable rheology compresses this distribution, reducing angular reflectivity and resulting in flat or weak flop. Travel describes the smoothness and continuity of color change between face and flop as the viewing angle changes. Technically, travel reflects the uniformity of flake orientation distribution and film microstructure across the surface. Disruptions in solvent evaporation, airflow, or application conditions cause localized variations in flake alignment, producing abrupt transitions, patchiness, or visual breaks during angle change. From a film formation perspective, solvent evaporation controls the time window during which metallic flakes can orient and redistribute. During the wet phase, flakes respond to gravity, surface tension gradients, and flow relaxation. As solvent evaporates, viscosity increases and progressively immobilizes flakes. If this transition occurs too rapidly, orientation freezes prematurely. If it occurs too slowly, excessive flow and gravitational effects disturb orientation uniformity. Viscosity evolution is therefore critical. Low shear viscosity governs post-application flake mobility, while yield stress development defines when movement stops. A narrow or unstable rheological transition window results in inconsistent face, weak flop, and poor travel. This is why rheology control in metallic basecoats is more critical than in solid colors. Solvent system design directly influences these outcomes. Fast solvents dominate early viscosity rise and affect face brightness. Medium and slow solvents maintain mobility necessary for flop development and travel smoothness. The balance across these fractions defines whether face, flop, and travel develop harmoniously or compete with each other. Measurement systems translate these optical effects into quantifiable data. Multi-angle spectrophotometers measure reflectance at defined angles corresponding to face, flop, and intermediate travel points. However, OEMs do not approve colors based on isolated values. They assess angular consistency, body-to-body variation, and stability under process shifts, recognizing that small changes in flake orientation produce visible differences on full vehicles. Production variability, such as airflow differences, body temperature variation, spray overlap, and line speed, shifts solvent evaporation and viscosity evolution. Metallic systems with narrow process windows show strong sensitivity in face, flop, and travel, often failing OEM appearance audits despite passing laboratory evaluation. For this reason, OEM approval focuses on system robustness rather than peak optical performance. RD&I teams aim to design metallic basecoats that maintain acceptable face, consistent flop, and smooth travel across realistic production conditions. In summary, face, flop, and travel arise from controlled interaction between metallic flake orientation, solvent evaporation, and rheology evolution during film formation. These effects are measurable, predictable, and engineerable, but only when formulation and process are designed together. If you have technical questions related to multi-angle measurement, flop tuning, travel smoothness, or OEM appearance acceptance, share them in the comments for discussion in future episodes.